Welcome back to the Deep Dive, where we deliver the crucial context on the technologies reshaping our world. Today, we are diving deep into the, well, frankly, massive universe of large language models. Things like Gemini, GPT-4, Llama, DeepSeek.
Absolutely. These models have just completely changed the game for AI.
Yeah, and the scale is almost hard to wrap your head around. We saw research noting there are like over 182,000 LLMs available just in the Hugging Face library alone.
It's staggering. A huge number of these incredibly powerful tools just available.
Exactly. But, that brings us to the core question in the research we looked at. If we've got all these amazing models, why aren't they, well, enough? Why are researchers suddenly so focused on combining them instead of just pouring everything into making one single perfect model?
That's really the central question here. And the research points to two main drivers for this whole LLM ensemble trend. First, there are still these persistent performance concerns. I mean, even the top-tier models, straight out of the box, they still wrestle with accuracy sometimes. And, hallucinations are still a thing. Plus, getting them perfectly aligned with what a human actually intends, that's not fully solved. They aren't flawless oracles.
Right, they can still go off the rails occasionally.
Exactly. And the second big reason is just how much they vary. LLMs have different strengths, different weaknesses. It comes down to their architecture, how big they are, the data they were trained on, and critically, the cost to run them.
Okay, so like one model might be brilliant at complex logic puzzles,
But way too expensive if you just needed to categorize customer emails, for example.
and a smaller, cheaper one might be fast for that email task,
Mm-hmm.
but maybe makes, I don't know, dumb mistakes on harder stuff.
Yeah, precisely. So the whole idea behind LLM ensembles, and it borrows a lot from traditional ensemble learning and machine learning, is to stop relying on just one best model based on some leaderboard. Instead, the goal is to use multiple LLMs together, really harness their unique strengths to get the best possible answer for a given query, often while keeping an eye on cost and efficiency.
Okay, makes sense, like a committee of specialists rather than one generalist. So let's unpack this. The sources laid out a really helpful taxonomy, kind of organizing these methods based on when the ensemble happens. Is it before, during, or after the model actually does its thinking, its inference?
Exactly. That timing is key.
Well,
Let's start with the two ends of the spectrum. Ensemble before inference and ensemble after inference. So ensemble before inference. This is mostly about being smart with resources, primarily cost. It uses a kind of traffic routing algorithm before any LLM inference happens. This router looks at the incoming query and decides, okay, which single model is the best fit for this specific job? It directs the query to just one model.
so it's like a hard vote. Pick one, and that's the one that runs. Keeps things cheap.
That's the main goal, yeah. Efficiency. Using the most specialized, often smallest, suitable model.
Does that router need to be specially trained for every different kind of task?
Good question. There are basically two flavors. You've got pre-trained routers. These do need custom training data. They use methods like classification or reward-based learning to figure out which model is good at which type of query. For instance, there's a system called Rutu. It first predicts performance, then applies a cost-aware filter to pick the final model.
Okay, so that needs some upfront work. What's the alternative?
The alternative is a non-pre-trained router. These use selection strategies that don't need that explicit pre-training step. One really interesting example mentioned is called Eagle. It actually uses the ELO ranking system.
Wait, ELO, like they use for chess rankings? Or, video games? How does that work for language models? It feels so subjective.
It's a clever adaptation. They're not using ELO for some absolute measure of goodness. They use it to figure out relative skill levels between the models. Basically, they run these internal tournaments comparing model outputs side by side for different query types. Over time, the ELO scores show which model are relatively better or worse in certain areas. And the system uses that dynamic ranking to pick a model that's likely good quality and fits the budget without needing constant retraining.
Huh, that's pretty smart. Agile. Okay, so that's before. Now let's jump to the other end. See ensemble after inference. So here, the ensemble magic happens after you've already gotten full answers back from maybe several models, or all of them.
That's right. You let the models generate their complete responses first. Then you figure out how to combine or select from those finished outputs. And within this after category, the first main type is C1, non-cascade methods. These basically integrate the multiple complete responses you got.
Okay, how do they do that integration?
Well, the simplest way is selection-based. Think of methods like Agent Forest or Smoothie. They often work on a kind of majority voting principle. But it's not just counting votes. They look at which response is most similar to the others.
How do they measure similarity between, like, sentences?
They use various metrics, sometimes BLEU scores, which compare n-grams, or they might encode the responses into vectors, numerical representations in space. Then they calculate something like the Euclidean distance between these vectors. If responses cluster together in that space, they're considered similar. The one in the biggest cluster wins.
Right, so find the consensus. But, doesn't that risk just picking the most average, middle-of-the-road answer? What if one model had a really creative or insightful answer, but it was different from the rest? Does it just get ignored?
That's a really important point and a potential downside of simple majority voting. It can suppress outliers, even if they're brilliant, which is why researchers developed more sophisticated approaches like selection then regeneration. LLM Blender was a pioneer here. It's a two-step dance. First, a component they call a pair ranker assesses the quality of all the candidate responses and picks out the best subset.
Okay, so it's not just similarity, it's also judging quality.
Exactly. Then, those selected best responses are fed into another model, a GenFuser generator. Think of the GenFuser as a final editor. It takes the best bits from the selected responses and synthesizes them into a single, polished, often better output. It's trying for intelligent integration, not just consensus.
That sounds much more powerful. Okay, what's the other type of after-inference ensemble?
The second major subclass here focuses heavily on efficiency again. These are C2. Cascade methods. The idea here is that you perform inference sequentially through a chain of LLM candidates. You typically order them maybe from smallest, cheapest to largest, most powerful.
What chain?
And the key is you have a deferral rule. This rule decides whether to stop early.
Ah, the cost-saving bit again. So the deferral rule is like a gatekeeper at each step in the chain. It decides, is this answer good enough, or do I need to pass it on to the next, bigger, more expensive model?
Precisely. If the current model's output meets the criteria set by the deferral rule, you stop the chain and use that output. If not, you defer to the next model in line.
What kind of signals does that rule use? How does it know if the answer is good enough?
Often, they rely on unsupervised signals related to the model's confidence. One common signal is class uncertainty, especially for classification tasks. If the probability the model assigns to its top predicted class is really high, above some threshold, the rule assumes high confidence in stocks.
Okay, high probability equals confidence. Makes sense.
Another signal is answer consistency. You might probe the current model with slightly different versions of the prompt. If it consistently gives the same or very similar answers, that suggests stability and confidence.
So if the cheap model seems sure of itself, either by high probability or consistent answers, you trust it and save the cost of calling the big guns.
That's the core idea, yes. Efficiency through early exit.
That concept of checking confidence and potentially stopping,
Yeah.
it leads perfectly into the next category, which sounds like the most intense approach. We're going from checking full responses or stopping a chain of models to actually intervening during the generation process itself, token by token, almost. Let's talk about ensemble during inference.
Yeah, this is definitely where things get the most granular and arguably the most complex, but also potentially where the biggest gains are. Ensemble during inference doesn't wait for full responses. It aggregates information from multiple models while they are still decoding, maybe at the token level or slightly larger chunks. And critically, it often feeds that aggregated information back into the models to influence the next token they generate.
Wow, okay. So it's like they're constantly checking in with each other as they write.
Sort of, yeah. Let's start with the finest level, B1, token level ensemble. This tries to combine information right at the individual token prediction stage, but they hit a major snag almost immediately. Vocabulary mismatch.
Ah, right. Different models might break words down differently, use different internal dictionary.
Exactly. One model might see transformer as one token, another might see it as transform and This makes it really hard to just average their probability distributions over what the next token should be because they aren't even talking about the same set of possible tokens.
Yeah, that sounds like trying to average apples and, well, slightly differently shaped apples that are also oranges sometimes. How do they deal with that?
It's a big challenge. They use some pretty clever aggregation-based methods. One approach, used by a method called GenAI, is to actually build a union dictionary, essentially combining all the vocabularies from the participating models into one massive dictionary.
Whoa, that sounds computationally heavy.
It can be. Then they project each model's probability distribution onto this shared merged dictionary so they can be averaged or combined. Other methods try to avoid creating that huge dictionary. Deepen and EVA, for instance, try to project the outputs into a shared relative or pivot space. It's like finding a common conceptual ground where the outputs can be compared and aggregated, even if the specific token words are different.
Okay, finding a common language, conceptually speaking. So a lot of engineering focus there on translation and unification. Now, you mentioned earlier this concept of perplexity, or PPL. I saw that pop up again in this during inference section. How does perplexity help decide which token gets picked at each step?
Right. Perplexity is really important here. Remember, it measures how surprised a model is by a sequence of tokens based on its training data. Lower perplexity means the sequence is expected, higher means it's unexpected.
So low perplexity is high confidence.
Essentially, yes. A low PPL for a given token suggests that, based on the preceding context, the model finds that token very likely it aligns well with what the model knows. So, during token-level ensemble, you can use PPL as a signal. If Model A has a very low PPL for generating token X, and Model B has a high PPL, it suggests Model A is more confident or expert in this specific context.
And methods like PackLLM use that signal to weight the contributions.
Exactly, or to decide which model's prediction to favor at that step.
And just like we had routers in the before inference stage, do we see routing happening here too, but like constantly at every token step?
We do. It's pretty wild. Seatter is an example that uses reinforcement learning for this. At every single token generation step, it makes a dynamic decision. Should we use the token generated by the small, cheap model, or should we trigger the larger, more powerful and expensive model just for this specific token?
Wow, micro-routing for maximum efficiency.
It's aiming for that sweet spot, yeah. Then, moving up just a little bit in granularity, there's B2, span-level ensemble. Instead of working token by token, this operates on slightly larger chunks, a span, which might be, say, forwards long or some other sequence fragment.
Okay, a bit less overhead than token level, maybe?
Potentially. These methods typically follow a kind of generate, assess, select pattern. Multiple models generate their candidate span. Then you assess those spans, often using perplexity or other scores, to see which model produced the most confident or likely fragment. The span with the best score gets selected and appended to the output.
Okay, that paints a pretty clear picture of the different timing strategies. Before, after, non-cascade and cascade, and during token and span. But it's easy for these terms to blur. Before we get into the takeaways, could you quickly clarify how LLM Ensemble differs from things like LLM merging or LLM collaboration? They sound related.
Good point. It's important to draw those distinctions. They are related, but different goals, different mechanisms. So LLM merging, sometimes called fusion, is about integrating the actual parameters, the learned weights and biases inside the models from different LLMs to create a single new, hopefully more capable model.
Right, so merging actually changes the model's internals. Ensemble usually works with the models as they are, combining their outputs.
Exactly. Ensemble typically treats the models as black boxes, more or less. Then there's LLM collaboration. In collaboration, you usually assign different roles to the LLMs. Maybe Model A drafts the text, Model B acts as a critic, Model C fact checks. They pass information back and forth, but have distinct jobs.
Whereas in most ensemble methods we've discussed, the models are kind of peers, all tackling the same user query, right?
Generally, yes. They face the query with equal status, and the ensemble mechanism figures out how to best use their responses.
That distinction is helpful, keeps the focus clear. Now, this field is moving fast, and you mentioned benchmarks are being developed specifically for ensembles.
Yeah, that's crucial for progress. We saw mentions of Mix Instruct, which is tailored for evaluating how well ensembles follow complex instructions, and importantly, Router Bench. This one is specifically designed to measure methods that have to balance both performance and cost.
Perfect for those ensemble before routing methods we talked about.
Exactly. It lets you rigorously test if your router is making smart, cost-effective choices.
So, stepping back and looking at all this research, what are the big takeaways? What does the evidence suggest about which strategies work best or what the trade-offs are?
The survey we based this on really synthesized some key findings. Two main themes emerged. First, granularity versus performance. There seems to be a trend suggesting that the finer-grained methods, especially token-level ensembles, because they intervene earlier and more often in the generation process, they can better harness the underlying probability distributions of the models. They can kind of nudge the generation process in the right direction, token by token.
So more control potentially equals better results.
That seems to be the potential, yes. It allows for more effective use of the model's internal knowledge, potentially leading to higher performance ceilings.
Okay, what was the second theme?
The second was about goals versus constraints, specifically the constraint of cost. The research indicates that methods not primarily driven by cost saving, like the ensemble during inference approaches and the non-cascade ensemble after inference methods, like LLM Blender, tend to have more flexibility. Because they aren't constantly worried about minimizing costs at every step, they can use more complex, potentially more powerful integration strategies.
Which gives them a higher potential for boosting raw performance.
Right. Whereas the methods explicitly designed for cost efficiency, like ensemble before routing and the cascade methods, they inherently face a trade-off. Their main job is to save money or time, which can sometimes limit how much they can improve the actual quality of the output compared to the best single model.
The classic performance versus efficiency trade-off.
Pretty much. You optimize for one, you might sacrifice some of the other.
It definitely feels like this is an area with a lot of active research and iteration. Where are things heading next? What are the big open questions or challenges researchers are focused on now?
Yeah, the field is definitely buzzing. The survey highlighted 3 key future directions that researchers are really digging into. First, for span-level ensembles, they need principled span-level segmentation. Right now, defining a span as just, say, 4 words is pretty arbitrary.
Yeah, seems crude. Language doesn't work in neat 4-word blocks.
Exactly. So the goal is to develop smarter ways to segment the text for ensembling, ways that respect semantic meaning or syntactic structure, not just fixed lengths.
Okay, more intelligent chunking. What else?
Second, there's a push for more sophisticated, unsupervised, non-cascade ensemble after inference methods. Remember, the simpler ones rely heavily on basic similarity metrics, and the more advanced ones, like LLM Blender, sometimes need extra supervised training data for their ranking and fusing components.
Which limits how easily you can apply them to new domains or tasks.
Right, so the ideal is to develop powerful methods in this category that work well without needing that extra supervision, making them more general purpose.
And the third area?
The third is developing a general unsupervised cascade approach. Most current cascade methods, the ones that stop early for efficiency, are really designed for simpler tasks like classification. They don't generalize well to complex, open-ended generation tasks like writing an essay or having a long conversation.
Ah, so we need a cascade approach that works for the kind of creative, generative stuff LLMs are increasingly used for.
Precisely. An unsupervised cascade method that's robust for open-ended generation is kind of a missing piece right now.
This whole exploration of LLM ensembles is really fascinating. It underlines that maybe the path forward isn't just about building one monolithic superintelligence. Instead, it seems like leveraging the diversity, the specialized strengths of many different models working together like a well-run committee might be the key to unlocking truly optimal, reliable, and maybe even efficient AI performance.
It definitely points towards harnessing collective intelligence.
So here's a final thought for you, our listener, to chew on. We heard about routers using ELO rankings, a system from competitive games to pick cost-effective models. Think about what it would really take in terms of model capabilities and routing intelligence for the smallest, fastest, most specialized model to consistently win that ranking, even for sophisticated, open-ended tasks. Cracking that optimization problem, getting peak performance from minimal resources, that might just be where the next big leap in practical AI lies. Thanks for joining us on The Deep Dive.